Welcome to the course Excelling with Mathematical Modeling. Today we will be talking about a drug delivery model in the discrete case. Let us define the model that suppose a patient is given drug to treat some disease, some infection, and he or she is given the same dose of the medicine at some equally spaced time interval. So, as you know, when the drug gets into the body, not the 100% of the drug works, a part of it works, and let that portion or part be R of the original amount of drug that is injected in the body. Our third assumption is after each dose, the amount of drug in the body is equal to the amount of the given dose plus the amount which is remained from the previous drug. So, if you want to model this, it will be x n plus 1, the amount that is remain from x n, that is the portion R, plus a constant amount of drug that is given in the patient at equal time interval. So, it is a very simple model. If you want to calculate the equilibrium solution, then we replace the x n plus 1 and x n by x star, because there is no change from n to n plus 1, and if you do that, you get R times x star plus b. So, x star into 1 minus R equal to b, and x star is b divided by 1 minus R, and R cannot be equal to 1. Now, let us derive this in another way. So, at x 0, which is 0 and it is no drug, and x 1 is b, which is the first dose. So, x 2, if I put n equal to 1 here, which is R times x 1 plus b. So, I get R times b plus b. So, this is the amount remained from the previous dose, and this is the new dose of drug that has been injected. So, I can write x 3 as R x 2 plus b. Now, R times x 2 is R b plus b plus b. So, if I write them, I will write it as b plus br plus br square. Similarly, x 4 will be b plus br plus br square plus br cube. So, just one less. So, in the similar manner, x n plus 1 will be b plus br plus br square till br to the power n. Take the b common, it is a GP series in R. So, the formula is 1 minus R to the power n plus 1 by 1 minus R, assuming R is less than 1. Because R is a fraction of the drug, so R has to be less than 1. So, as n becomes large, so what you see is that your x n plus 1 tends to the value b divided by 1 minus R, because this will, since R is less than 1, this quantity R to the power n plus 1 will tend to 0 as n becomes large, or it tends to infinity. So, for large time, it reaches a steady value b by 1 minus R, which coincides with our equilibrium solution, and we can see that it is stable. Let us now take a different scenario. We assume that amount of drug in a patient's bloodstream decreases at a rate of 80% per hour, and an injection is given at the end of each hour that increases the amount of drug in the bloodstream by say 0.2 units. So, if you want to model this, so A n plus 1, that will be A n, the drug is decreased by 80%, so 0.8 A n plus 0.2 units of the drug or in the form of injection is added to the patient. So, if I want to simplify, I will see 0.2 A n plus 0.2. So, the previous model was in this form, that is A n plus 1 equal to R times A n plus some p. If you want to find the equilibrium solution, you can easily put A n plus 1 equal to A n equal to some A star, and you will get A star is equal to 0.2 A star plus 0.2, and you can calculate 0.8 A star equal to 0.2, and your A star is 0.2 by 0.8, 1 by 4, 0.25. So, this is your equilibrium solution. Let us take another example. So, we assume that a certain drug is effective in treating a disease if the concentration of the drug remains above 100 mg per L. This L is some plasma concentration. It is a unit commonly used. Say initial concentration is 640 mg per. The drug decays at a rate of 20% of the amount present each hour. So, if I take Cn, that will be Cn minus 1 minus the 20% of the drug is less each hour, and this will be equal to 0.8 Cn minus 1. So, I can write this as 0.8. So, this Cn minus 1 can be written 0.8 Cn minus 2. Similarly, this Cn minus 2 can be written as 0.8 Cn minus 3 and so on, which is 0.8 cube Cn minus 3. So, in general, Cn will be 0.8 to the power n. So, if I replace this by n, this will be replaced by n and this will be C0. So, C0 is the initial concentration that is given, which is 640 into 0.8 to the power n. So, the question we pose here is at what hour the concentration of the drug reaches 100 mg per L. So, please note the problem says that the drug is effective if the concentration of the drug remains above 100 mg plus L. So, we want to find in how many time or how many hours that concentration of drug will reach 100, provided it follows this particular model. Let us quickly see the numerical solution of this particular model using Microsoft Excel. So, as you can see, this is the model which has been discussed previously, that is a n plus 1 is 0.2 a n plus 0.2. So, I have taken two initial conditions 0.1 and 0.5 just to see how it will look. So, this is equal to 0.2 multiplied by a n, which is this, plus 0.2. So, I get one value, and this is equal to 0.2 multiplied by a n plus 0.2. So, if I just highlight them and calculate the values. So, if I just plot these 10 values, I will see a graph like this. So, in this particular problem has an equilibrium point as 0.25, and you can see that no matter from whatever initial condition it starts, it reaches the value 0.25, implying that the system is stable about the equilibrium point. Now, coming back to the recent problem where it says that you have a concentration of drug and you have shown that the model is C n, which is equal to 640, the initial value, multiplied by 0.8 whole to the power n. This is the model which we are discussing about. So, what we have to find, that it says that the drug concentration cannot be less than 100 mg per L, some plasma concentration. So, we want to find it from the graph, what is the time that will make the graph of the drug to reach that 100 ml per L. So, what you do here is, this is the initial concentration, this is equal to, you put 640 multiplied by 0.8 to the power n, which is 0 here, enter. So, you get 640 and I drag it, say up to 30 values. Now, this is 100, I keep it the constant value 100 because I need a straight line. So, all of them are 100. Now, let me plot this. This is 0, I highlight till 30 values. When you click the control, you press this, you press shift and the down cursor. So, it will highlight this row, this column, again press control, select this, press shift and the down cursor. So, these through columns have been selected. You go to insert, go to the chart, see the chart. So, what you see here is that this is the drug, the curve, and it goes to 0, and this is the line of 100 ml, 100 mg per L. So, this is the point of intersection, and that value is approximately equal to 9 time unit. In this case, it is hour. So, approximately in 9 hours, the concentration of the drug will reach the 100 mg per ml. Let us now go back to our slides. So, the answer to our question, at what hour the concentration of the drug reaches this 100 mg per L, is approximately 9 hours, which we have shown by solving this model numerically. The next part is, what is the maintenance dose that will keep this drug above 100 mg per L and below 800 mg per L. So, how much drug you should give? It should have a range such that it always lies above 100 mg, which is required for the drug to be effective, and below 800 mg per L, so that there is no overdose. So, for that you go back to the model, which is Cn equal to 0.8 Cn minus 1, and we have our x. Suppose x is the dose. So, if we want to find the equilibrium solution, we will replace this by C star 0.8 C star plus some x. So, our x is 0.2 C star, which implies C star equal to 5x. Now, this value should not cross this 100, and it should lie between this 100 and 800. So, you have 100 less than 5x less than 800. So, this will imply that 20 must be less than x must be 160. So, the dose that you want to give to the patient such that the drug concentration is never below 100 and never cross the value 800 is that the dose must lie between 20 and 160. Let us quickly see the numerical solutions. So, this is the one which we have shown in Microsoft Excel. So, it says that this value reaches 0.25, it starts with an initial condition 0.5 and 0.1, but since the system is stable, it goes to the value 0.25, which is the equilibrium solution. In this, it is shown that this is the concentration of the drug, which was Cn equal to 640 into 0.8 to the power n, and we have plotted this, and this is the line for 100 mg per L. So, both intersect somewhere here, and it shows that approximately 9 hours will be needed so that the concentration of the drug reaches 100. And finally, this one is where we have shown that the range of the constant input of the drug must lie between 20 and 160. So, this particular figure shows that it starts with an initial condition which is 640, and the amount of drug here is 10, 40, 120 and 200. So, what will happen that if this concentration of drugs is maintained, so if it is 10, as you can see that it is going down below 100, whereas if it is 40 and 120, it lies within the range, and if it is 200, it will go beyond. We now take another example. Say a person with an ear infection takes 150 mg ampicillin tablet once in every 4 hours. So, that is the time interval. About 15% of the drug in the body at the start of a 4-hour period is still there at the end of the period. So, a person with certain ear infection, he takes 150 mg of ampicillin tablet every 4 hours, and 15% of the drug is in the body in this 4-hour period. So, the first question which we ask, what quantity of ampicillin is in the body right after taking the third tablet. So, as we have modeled this before, the model equation is xn plus 1 is Rxn plus B. So, R is the amount of drug which is present in the body. So, in this particular case, R is 15%, which is 0.15, and the dose every 4 hours is 150 mg. And we have shown that this is equal to B times 1 minus R to the power n plus 1 divided by 1 minus R. So, after taking the third tablet, we have to calculate x3, that is by putting n equal to 2, and we get this is equal to B 1 minus R to the power 3 divided by 1 minus R. So, B is 150, 1 minus 0.15 cube divided by 1 minus 0.15. So, this gives you 150 into 1 minus 0.003375 divided by 0.85, which is 150 into 0.996625 by 0.85, and which gives 175.875 milligram. So, the quantity of ampicillin tablet which is in the body right after taking the third tablet, the amount of ampicillin is 175.875 mg. Next, we pose another question. Say, what quantity of ampicillin is in the body at the steady state level right after taking the tablet. And second question is, at the steady state level right before taking the tablet. So, the first question is, what is the quantity of ampicillin in the body at the steady state level right after taking the tablet? And we know that the equilibrium point or the steady state is obtained by replacing n plus 1 and xn to be x star, as there is no change from n to n plus 1. So, this gives Rx star plus B, which implies the value at the equilibrium point or at the steady state level is B by 1 minus R, which is 150 divided by 1 minus 0.15, and this value is 176.47 mg. So, the quantity of ampicillin right after taking the tablet at the steady state level is 176.47, and the quantity of ampicillin at the steady state level before taking the tablet, it's going to be X star minus B. So, this is the dose which you take every 4 hours. So, just before taking the tablet, that is the steady state level, minus 150 mg will give you the amount of ampicillin in the body at the equilibrium point or at the steady state level before taking the tablet. Let's now solve this model or this particular problem numerically using Microsoft Excel. So, I already have the equation xn plus 1 equal to rxn plus b, where r is 0.15 and b is 150. So, I have n and I have x. So, we put here n equal to 0. The initial value here is 0. So, we increase here by 1 and drag this to a few values, and this value is equal to r multiplied by xn plus b. So, the value of r is constant and the value of b is constant. So, I put a dollar and enter. So, I drag it to some values and then I plot this graph, go to insert, go to chart and click this. So, this is, you can write drug delivery model. We remove the grid lines, go to the axis title. This is the time and this is the amount of ampicillin. So, as you can see that this value over time reaches the value 176.47, which matches with our analytical result. So, with this we come to the end of this lecture where we have shown the discrete case of a drug delivery model. In my next lecture, we will be talking about compact models, namely discrete Lanchester's compact model. Till then, bye bye.